Please welcome Truman Boyce.
Hi, I'm Truman. I'm with Bloomberg. And this conversation today is one of philosophy and networking, kind of combining the two. So reduce, reuse, recycle. So reduce the complexity, reuse the technologies that actually make sense, and recycle the rest. So a little bit about our company. So Bloomberg has been founded in 1981 by Mike Bloomberg and his other partners. We're about 19,000 employees, and we have about 4,800 technologists that are working on our financial applications and maintaining the infrastructure. For better or for worse, we run and maintain our own IP/MPLS network. It's a global network, and at this point, it would look something similar to a traditional service provider network that would be, the standard protocols, all the complexity, lots of VRFs, lots of VPNs. There's different types of data that we carry. So we have everything from market data, video streaming between our different broadcast houses, voice communication for the company, screencasting so we can work with the traders, exchange connectivity as well as embargoed data, and there's lots and lots of multicast, unfortunately. We're about 15,000 CPE devices, so in total the network would look about 15 to 20,000 routers in total. But the conversation that I wanted to relate to you is one of complexity. At this point, we decided to take a look at everything that we do, the way that our network is built, the technologies that we use in-house, and we started to think that whenever you find yourself on the side of majority, it's time to pause and reflect. And this goes along with all the data center networks that have been built over the last 20 years. You look at a classic data center network 15 years ago, it was going to be the core distribution access style network. It was quite traditional in the protocols that it used, lots of resiliency added, then spanning tree protocols. And then if you looked at networks that we've been building, that we've learned from most of the modern companies, they're also starting to look similar. Folded class topologies, all L3. My point is, those are good, and this is the right building block to build on, but we still need to consider what is truth in our environment. Some of these things actually need to be questioned. I mean, even the idea that BGP in the data center, and albeit I think it's a great idea and a good stepping stone forward, is something that we should continue to keep questioning, is this the right choice? And what I mean by that is you take a look at these technologies and you look at BGP path selection and all of the different steps that have to go through simply installing a route into your FIB. How does a autonomous system number that happens to be unique on an individual leaf switch actually relate to just trying to connect a bunch of things in your data center? So this is really around the tenets of building a network. The way I think of it is networking is extremely easy. It's advertise all the things. It's make the vectors available. Security is also easy. It's actually the inverse of networking. It's let me take the things that I've already said can communicate with each other and dial it back. But when you mix the two together, it actually gets really, really hard. Take, for example, microservices today are lots of TLS 1.3, 1.4 connections, lots of microservices that are starting to connect everything, and yet we're still trying to solve this matrix of communication with ACLs, whether we distribute it or whether we actually decide to put this in big artificial pooling of resources throughout the rest of the network. It's actually doing it in the wrong way. If you think about the security layer today, a single port of 443 being open with an HTTPS connection is everything. It's the equivalent of IP any. So you need to rethink how you're actually doing your security in your environment. Sometimes the goals are conflicting, and this has happened across our data centers. We decided, okay, do we want to have an automation system that allowed port 1 to be different than port 47 on an individual top-of-rack switch? Now, these are the kind of questions that can be asked of you by your teams. They can say, look, I have a dev machine, I have a prod machine. You should make your network as fungible as possible so that I can individually move this arbitration of code around, and I can decide to contain various blast radiuses. So you could take that model, or you could take this other model where you say, look, I'm going to roll 30 machines on a rack. I'm going to push this rack in. I'm going to plug in the top of rack, uplink ports to my spine, and I'm done. And I decide to make a simple networking paradigm where a /24 and a /64 IPv6 address simply live on every top of rack switch, and that's all you need. The role that we have and the way that we view the network is that there really should be no slow data path elements. You take, for example, any top of rack switch today, choose any of them, whether it's Tomahawk, some of the new Broadcom stuff, or Barefoot, you're looking at least 3.2 tera and up of east-west potential capacity on every element. And yet, what's the fastest firewall that you can buy? In the hundreds of gigs? So you have these artificial pooling constraints that actually affect the way at which your entire business operates. We think about this when we go and purchase the latest i7s or the fastest computers out there with the most number of cores. Can I put them to use? If I have artificial pooling throughout my environment, the answer is no. I cannot put these things to use. So all of this investment that's going into high-scale, high-performance computing is not able to be utilized if you don't have a network that's also high-scale. Managing it. So, we firmly believe SNMP should die. It's neither simple nor a management protocol. So we're very interested in, the future of what that will look like going forward. And there's, various technologies and working groups that are starting to make some changes into that area. The other is more fundamental, in that network engineers have consistently, we've thought about blast radiuses and containment in networking speak. So we would think that this subnet is different than that subnet. This VLAN is different than that VLAN. They're just labels. It's just information. It's just metadata that can be used in building a model which would actually allow you to have some level of enforcement or some level of reachability. And the other one is being multi-vendor. We've always been multi-vendor, but this approach now is we're trying to disaggregate where it makes sense, and in some areas where there's best-of-breed technology, we're happy to deploy commercial vendors in those spaces that have proprietary technologies. So building an IP MPLS network, it made sense over time, but we're starting to dial that back. You think about the number of protocols required just to form basic communication. Multi-protocol BGP, you have route reflectors all over the place. Put multicast in it, and you have PIMs, sparse, dense, MSDP, et cetera, et cetera. It just gets more and more complex. There's so much happening. So when you have one failure, how long does it take to troubleshoot and find out what's actually happening? And we've seen this. We've seen a simple networking error that basically affected 2 minutes of forwarding on an individual node. And during that period of time, we ended up having the entire bond market was not able to be liquid. By that simple outage, it ends up causing an issue where many, many machines continue to fail in a cascading way, because the interrelationship between networking and complex message bus systems on top of it create this situation where it's very difficult to dig yourself out. So our thought is that our preferred NCAP, and believe me, I'm definitely a part of NVO3 and working through all the different methods on how we want to use NCAPs where it makes sense. But our preferred NCAP is just IP. It's just simple. We just understand, here's a machine, here's an address, I can take a look at a packet on the wire. The concern that I have with many levels of encapsulation, and as networking people, we love to encap things and put them into different tunnels all around the place. The challenge is that explaining what's happening is extremely difficult when things go wrong. We're trying to think about building the entire data center as Lego blocks. So, we've moved away from this model where, you'd get teams that would ask for individual machines, and we'd have to go and procure them and bring them in and roll them into the data center. Now it's just rack at a time. You want to think of these as an entire block that if it were to fail, that's okay. That if that entire rack disappeared, that's okay. Because we're using technologies on top of it above networking, which would allow you to suffer limited failure and your service itself. We're trying to move away from is that machine available and is that IP address available to is that service available. The other aspect is within the engineering teams is having our engineers build the robots and having the robots build the network, as opposed to all the artisanally crafted configurations that we've kind of grown up with, logging into routers and making changes. I had mentioned our multicast, and it's definitely been extremely complex. I think both sides of the aisle would agree. We're definitely trying to make some significant changes to reduce the complexity of multicast. Yeah. It is sad. the use of multicast in financial networks is for basically two reasons. One of them is the right reason. The main reason why it is useful is because you get fairness. And so the idea behind having multicast transmissions for lots of receivers is so that you can have market transparency, so that you don't have arbitrage. The wrong reason is that it becomes extremely simple to have a group of machines communicate with each other easily. And this is, poor application practices have actually forced networking people to do some really, disastrous things to their environment. So the challenge with multicast is the amount of state. I think as a goal, we're trying to reduce any state in the network so that it just becomes a simple fat pipe, and it's dumb. It's the same as what you'd get from any of the cloud providers. An area of interest has been network buffering. So, in the academic world, there's so many different algorithms to deal with congestion and to look at random dropping and other types of technologies like Codel. It's actually forced our purchasing decisions because we were afraid of dropping packets. And what we're realizing is actually, I think we've been looking at this problem in the wrong way. This is a networking-focused way to try to deal with an application that really should be dialing itself back, as opposed to continuing to throw expensive switching gear, which has deeper buffers in it. Now, there's a real use case for some deep buffers for some applications, and so it does make sense to look at various chips that would accommodate that. But we've actually been spending a lot of time looking at data center TCP and other technologies that are similar, that allow your applications, or purely at the Linux level, to pace the traffic appropriately so that you don't have drops in your traffic across the backbone. And the main point of that is that TCP, it's going to use all of the traffic that it has available to it. And in the current iterations, with most of the algorithms, it actually is not suitable. It will have congestion, but if you can look at data center TCP, you get to these steady states where all of the capacity that you've purchased, all of those 100 gig links, you're actually able to utilize, instead of this sawtooth behavior where you burst up and you start consuming the link only to then drop off and move to multiplicative decrease. So our philosophy, and this is one of the challenges I think a lot of enterprises that are our size face. I think the way that the narrative behind it is, I'm special, and my needs are different. And so the technologies that are being used at, the FANG companies and other may not relate to me. I mean, these conversations come up constantly. Do we really want to just build this thing ourselves, or do we want to use these open source technologies in our environment? And how do they relate to us? And should we actually continue to build some of these things in-house to have a key differentiator? I don't think these technologies, at least in the networking side, are going to be so unique to our company. So we've actually kind of shifted that if it's something that we can grab off of GitHub, if it's something that we can get with an awesome technology partner and we can put to use immediately, I'd much rather spend the time testing it, bringing it into the network, starting to spend some time with evaluating if it's the right technology for us, versus trying to figure out, do we need to put this through a standards body in ITF and get behind a vendor. And I just want to think, how quickly can we actually move to bring this in-house and to move our business along? The other concept is around black boxes. So they're bad. It's definitely, any kind of magic that we're not able to explain, we don't want to see it. And this goes with even in the commercial technologies as well. So if it's able to be explained, it's good. If you can't explain it, it's bad. So where it makes sense to use open source. So we've actually embarked on a road where we're starting to contribute significant amounts of our technologies back into open source. So we have our own GitHub repository. But we're also seeing an area where there are many different technologies that we want to bring in-house, and we will contribute back. So this is a change in the financial world. I mean, for the longest, it was the code that's written in-house does not leave. But we're realizing now that, especially with even attracting talent and being able to make changes, to our massive code base, and also be able to share with the community so we can have community support, we're starting to contribute back. The other piece that we were thinking about is that, processors, they're not really getting faster. You're getting more cores, aside from, GPUs are getting a little bit faster. But for us, cloud is the only way to scale. And when I say cloud, I'm not saying just, external cloud, but just cloud as a technology. It's the only way that we can actually build our business. And so we're very, very interested in, I'd say it's not just public-private, it's seamless cloud. So what I want to get to are the places where we don't have to worry about where is this workload actually running, but it's simply, I want to deploy this workload and the engines will figure out where this thing needs to run. So we never want to strain capacity. This has been a huge issue in just even starting to build clouds. Initially, clouds are built with different domains in mind. This is a dev cloud, this is a prod cloud, this is a internet-facing cloud. And the challenges with this approach is that you get to a place where you have this unnatural pooling happening, not just at the networking level, but now even your cores are kind of constrained all over the place. And so when you have a job that comes up that has to span across all of these different machines, you don't have the easy way to make that happen. The network is usually one of the biggest challenges on how these things are able to connect with each other. So if we have workloads that need to move around, we want to have the network just provide transport. So the areas that we're looking at, absolutely layer 3. So all layer 2, aside from the multicast replication side of things, is definitely moving all towards layer 3. BGP where it makes sense to connect top-of-rack switches and standard folded class. The private cloud internally. And then in the IP storage world, so we're doing lots of S3 object storage, as well as block emulation. But on these machines, it's pretty amazing. Like we're already connecting on standard x86 PCI Gen 3 systems with multi-100 gig NICs, and this